Okay, hello. This is the second question from the final exam. This is the standard linear regression model. We now have intercept, and we have exogenous variable. We have endogenous variable, as usual. So we have exogeneity condition for intercept and x1, but the endogenous variable is uncertain. Here, I'm asking you how to estimate this regression model with endogenous variable with instrument here. So as you may know, there are two different methods, two-stage least squares or GMM. First, I wanted to say that two-stage least squares and GMM are in the end the same, right? In like under some conditions like homoscedasticity. But I want you to understand like what's their benefits and like disadvantages. Right? In this question, I will recommend GMM because two-stage least squares would be easier to implement on software, but because you can just repeat OLS twice, then you will get two-stage least squares. But as I told you in class, this is more complicated variance derivation, right? So if you're doing software, they actually have built-in commands for their variance. So usually it does not matter in practice. But when you answer this kind of questions, obviously GMM is much better, right? Because the variance derivation is simpler, right? You learn a lesson if you just want to study simple things, then in the end, actually, that is more difficult. Okay, and also GMM is very general class of estimator, but two-stage least squares is very much limited to only linear cases. So I just, as a theorist, I recommend GMM better. And one more comment. Here, I define this kind of notations, but I realize it's not optimal because our equation is yi equals alpha 0 plus beta 1 0 x 1I plus beta 2 0 x 2I plus epsilon. So the reason why I define that notation, vector notation, is to write it as xi transpose, say, theta 0 plus epsilon. To write it this way, actually the definition should have been like my x usually looks like too much like alpha. Anyhow, the definition should have been intercept and x1, x2. And of course, theta must include the intercept. Okay? You like extending this intuition, actually the instrument z also had to include intercept and exogenous variable and excluded instrumental variable, right? This is a better notation. Or alternatively, you can think about demeaned variables, right? So you may redefine, say, for example, yi tilde is yi minus its mean, its sample average, and like x1 tilde is x1 minus its sample average. Like this way, then in homework 1, we learned we can rewrite the equation as something like this. Right? Just simply we are deleting the intercept. So this is another way. In this case, you have to define x as x1 tilde and x2 tilde without intercept. And theta is simply beta 1 and beta 2. So usually intercept is not that important in estimator. And by the way, also extending the idea, you need to think about z2 tilde as a demeaned variable. Okay, So everything is the mean. Everything, all the variables have zero, mean zero. So you don't need to worry about the intercept. But it's your choice. But let me just stick to this case, right? GMM, it's not a big problem in GMM. Later in maybe in the next video, I'm going to show you the two-stage least square version of the solution. But in GMM, intercept is not a big problem. Okay. So then now let's think about GMM. So then the moment function theta. Remember, theta is alpha and beta. Theta is defined. The moment function is defined this way, right? Pretty much the standard moment condition, and then we are going to define estimator theta by minimizing weighted distance of the sample moment using a weight matrix W. Okay, you must be familiar with this form. And in doing this, we define this kind of notation, like say omega was defined as expectation of gi theta 0, the true theta, times g transpose theta 0. Basically the variance of gi, which simplifies to epsilon I squared zi transpose, right? It is a matrix. And under homoscedasticity, you can write it as this. It is your choice if you make homoscedasticity assumption or not. And if so, a homoscedasticity assumption implies sigma squared is this. So for any z, the conditional variance of epsilon is sigma squared. That is homoscedasticity. Then you can separate sigma from z. That is common notation. And let me add another page. And then we also define g as the derivative at the true value. Here I had to transpose here. It is pretty simple again, zi xi prime. So everything is pretty simple in GMM. And then based on this notation, we know that the optimum weight should be omega inverse. Okay, so how do we implement this? So this is just theoretical optimality. So we have to study how to implement this optimal weight in practice. And so there are several methods. First, you can think about two-step GMM. Like it does not require homoscedasticity. Okay, in this case, first use identity matrix as weight and wait for the GMM and obtain a preliminary estimator theta tilde, which is consistent, right? You will get a consistent, which is consistent. But it is consistent, but it is not optimal. Its variance may be bigger than the optimal. And then calculate epsilon tilde using the consistent estimator. So yi minus xi transpose theta tilde. And then calculate this guy, right? Because we don't need homoscedasticity, we can estimate this and estimate that part using sample mean and use calculated epsilon and observed z, right? So this will be your estimated, of course you have to take inverse of that. This is what you can calculate. You can calculate, right? So compare this. You cannot calculate this because of epsilon. Epsilon is unobserved, and also expectation requires infinite observations, which are impossible. So because of these two guys, we cannot implement this theoretical weight. So we replace epsilon with its estimator, right? And also we only use finite sample, sample average instead of the population expectation. Okay, this is how you can implement the optimal GMM. Or another page. Or another way is under homoscedasticity, the optimal weight is its inverse, right? So homoscedasticity allows you to separate, like factor out sigma squared, then and to be more exact, your optimal weight is not just equal, but your optimal weight is proportional, because multiplying a constant, a positive constant, does not change the minimization problem. So your optimal weight just is required to be proportional to this guy. So that means you can set W as its inverse because it is constant, because this is positive constant, right? It's not required. And how will you implement? So this is your theoretical, now new theoretical optimal weight, right, under additional assumption. Then you implement W as same way, right? Z prime are observed that they don't have any problem. Just replace the expectation to sample average. That is how you implement the optimal weight under additional assumptions. So remember, it depends on the homoscedasticity assumption, but this two-step GMM does not require homoscedasticity assumption. So that is your choice. Now then, let's think about the asymptotic variance. It's actually easier. We learned if omega is, if W is omega inverse, I'll assume omega inverse, right? Then the variance of asymptotic variance of theta hat is given as G transpose omega inverse G total inverse. Okay, that is what you have. And remember, G was defined as ZX transpose, and also remember omega was defined as expectation of epsilon squared times ZI transpose without homoscedasticity. Then how would you implement that? It is easy. You estimate G hat as minus the sample average of the observed variables. Okay, and then how do you do that? How do you estimate omega? That is defined as sample mean, and instead of epsilon itself, we use residual epsilon hat and ZI transpose. Okay, so here this epsilon hat is this residual, right? Straightforward residual. The difference from the earlier part is this residual requires estimated GMM estimator, but when you implement two-step GMM, you have to calculate the residual before calculating the final GMM estimator. So you use instead a preliminary estimator which is still consistent. So that is the difference. Because so again, the variance, say weight matrix should be calculated before estimation, right? But variance matrix is calculated after you estimate theta. So this is the difference. Like, because after the estimation, it is much easier because you know you have an estimator for the unknown parameter, but before the estimation is a different story, right? Oh, delete it. So that's another thing. And this is how you implement variance. This is the answer. In a separate video, I'm going to show you two-stage least squares solution, which is much more complicated. I'm not sure if I can finish it. Anyhow, thank you for